This lecture on the topic steady flow energy equation. Steady flow energy equation. In short, this is written as SFEE, double E, SFEE. You will find this topic in the chapter of first law of thermodynamics applied to flow processes. So far you have studied first law of thermodynamics for non-flow process. Non-flow process means where there is a closed system and inside the closed system there is some fluids. The fluid may be liquid, it may be gas also. Okay. So what was the first law, mathematical form? It was Q minus W is equal to U. Rather I should say delta U. Q means net heat applied to the system. Applied or supplied to the system. Not applied, supplied to the system. Net heat supplied to the system is Q. For example, heat supplied to the system is Q in and heat dissipated by the system is Q out. Therefore, net Q is equal to what? It is Q in minus Q out. That is the net heat supplied to the system. And net heat supplied to the system is taken as positive. Okay. Or heat supplied to the system is taken as positive in engineering thermodynamics. And for work done by the system is taken as positive. So say for example, for this case, you assume that total work done by the system is W. Therefore, Q minus W is the net energy transferred to the system. Work is also a form of energy. So net heat supplied to the system is how much? It is Q minus W. Net heat supplied minus total work done by the system. So that is the net energy supplied to the system, and this net supply of energy to the system will increase the internal energy of the system. So say U denotes internal energy, therefore delta U will be the change in the internal energy of the system. So this was for closed system. Now we are talking about, in this chapter, we are talking about flow processes, means where there is fluid and it is flowing. So now we need open system since there is fluid flow involved. So we need open system, means there is one system. Say, for example, there is one container or a drum. Drum is also a container. There is one container, there is one inlet to the container through which fluid will be entering into the system, and there is one outlet attached to the container from where the fluid will leave the system. One inlet, one outlet. You can generalize this. You may take so many numbers of inlets, so many numbers of outlets. But for simplicity, we are taking just one inlet and one outlet. Now, through the inlet, fluid will be entering into the system, and through the outlet, fluid will leave the system. When fluid is entering into the system, the fluid needs to do some work for entering inside the system. And when fluid is leaving the system is doing some work on the fluid. This is known to you. System must do some work on the fluid. Otherwise, it won't be possible for the fluid to leave the system. Okay. When fluid is flowing, you know that since it is flowing, it has some velocity. So it should have kinetic energy. It has some elevation with respect to a chosen datum. So it should have potential energy with respect to that chosen datum. It should have some internal energy. Internal energy is what? Energy content of the system. So it should have some internal energy. Okay. There may be heat supply to the system, net heat supply to the system. There may be work transfer from the system or net work done by the system. So all these things may be present at a time. Now, steady flow energy equation. The term steady has been used here. Steady means what? The property of the system won't change with time. Property of the system won't change with time means property of the system will remain constant with time. They won't change. So that is steady flow energy. The term steady defines that thing. And steady flow energy equation. So this is one energy equation. So to get this energy equation or to derive this energy equation, we need to do energy balance. By using the principle, energy can neither be created nor be destroyed. Using this principle means total energy will be conserved. So using this principle, we will derive energy equation. One more thing means one more equation or one more principle that needs to be used here, that is conservation of mass principle. The first one was conservation of energy principle. Energy can neither be created nor be destroyed. And the conservation of mass principle means mass can neither be created nor be destroyed. So there is one inlet, there is one outlet to the open system, at last to the open system. So say inlet section is denoted by 1, and outlet system is denoted by 2. Suffix 1 and 2 will be used. Say inlet area, cross-sectional area of the inlet is A1, A suffix 1, capital A1, and outlet surface area is A2. Similarly, density of the fluid at inlet section is rho 1, density of the fluid at outlet section is rho 2. Velocity at inlet section is C1. We are not using V1 because in thermodynamics V will be used for volume. So instead of writing V, you write C. Okay. So C1 is the velocity of the fluid at inlet section and C2 is the velocity at the outlet section. And you know that rho into A into velocity, density multiplied by the cross-sectional area multiplied by the velocity, that is what? That is mass flow rate. And that is equal to constant for one-dimensional flow. We will use here one-dimensional flow concept, not 2D or 3D. Just for simplicity. Okay. So density multiplied by area multiplied by velocity, rho A V. So instead of V, we will write C. So rho A C is constant. Therefore, rho 1 A1 C1 is equal to rho 2 A2 C2. And here in thermodynamics, instead of writing rho, that is density, we will replace this density by specific volume. You know that specific volume is reciprocal of density. Therefore, rho 1 is what? It is 1 by V1. Rho 2 is similarly, it is 1 by V2. Therefore, rho 1 A1 C1 becomes A1 C1 by V1 small v. Specific volume is denoted by small v. So, rho A1 C1 area into velocity divided by specific volume. A1 C1 by V1 is equal to A2 C2 by V2. So, that is this is mass flow rate and this is constant. That's why they are equal. Now come to energy equation. So we are simply assuming that Q is the total heat supplied to the system, net heat supplied to the system, and W is the net work done by the system. Okay. And So energy at inlet, it is equal to will be what? So first you draw one container, at one elevation you draw the inlet section, at other elevation you draw the outlet section, draw one datum. With respect to datum, draw the elevations. Say elevations are denoted by Z1 and Z2, like that. Area by A1 and A2. Specific volumes by V1 and V2, small v1 and small v2. Velocities by C1 and C2, like that. Okay. Pressures by P1 and P2. So at inlet section there is kinetic energy. Now suppose you have got mass flow rate. Say mass flow rate is denoted by m dot. M, and above m you put one dot. So this dot denotes mass flow rate. M dot denotes mass flow rate. So what is the kinetic energy flow rate? Rate of kinetic energy at inflow section or inlet section? It is half mv square. M is mass, total mass. Half mv square divided by time. So this m by time is what? M by time is m dot, mass flow rate. So half m dot into C1 square. Half m dot into C1 square. This is the kinetic energy flow rate at inlet section. Similarly, potential energy at inlet section, it is mg z1 divided by time. Again, mass by time is equal to m dot. So potential energy flow rate is equal to m dot g z1. So this way you have to proceed for the calculation. Next is internal energy. So m dot is the mass flow rate. Suppose small u denotes specific internal energy. So for inlet section it will be u1, small u1, and for outlet section it will be small u suffix 2. So mass flow rate multiplied by the internal energy, that will be the total internal energy in time delta t. Total time interval we are considering, it is delta t. So m dot into small u1, this will be the internal energy flow rate at inlet section. M dot u1. So we have got kinetic energy flow rate, potential energy, and then rate of potential energy, and then rate of internal energy. Similarly for outlet sections, all these things will be written but with suffix 2. Now heat, net heat supplied to the system is Q in time delta T. In time delta T, net heat supplied to the system is Q. Okay. Now, so total energy is equal to what here? It is equal to kinetic energy at inlet plus potential energy at inlet, plus, means all these things are in rate form: kinetic energy rate, potential energy rate, then internal energy rate. Okay. Then Q is the heat supplied in time delta T. Okay. So in time delta T, what is the total kinetic energy plus potential energy plus internal energy rate? It is equal to, you take summation of all these three and multiply it by delta T. Summation of kinetic energy plus potential energy plus internal energy multiplied by delta T. That will be the total energy inlet in time interval delta T. And in time interval delta T, net heat supplied is Q. So at inlet, kinetic energy flow rate is same thing, but suffix 2 will be used there. Then comes work transfer. Work done by the system, suppose it is W. So at inlet section, since fluid is entering into the system, there is work done. But here fluid is doing work on the system. So that work done will be negative, and you know that this work done is equal to product of pressure and volume. So at inlet section it will be P1 V1, but with a negative sign you have to write, since it is work done on the system. At outlet section, work done will be what? It will be again PV, product of pressure and velocity. V. We should use C. Yes, it is volume. We should use V, not velocity. Pressure and volume, V2. P2 V2. So plus P2 V2, that will be the work done by the system at the outlet. And suppose shaft work or the work done by the control volume is equal to WCV or W suffix shaft. W suffix shaft, SHAFT, shaft. That is the work done. Therefore, total work done is equal to, by the system, is equal to minus P1 V1 plus P2 V2 plus W shaft. Right. So in the left hand side you write summation of kinetic energy plus potential energy plus internal energy multiplied by delta T plus Q. In the right hand side, summation of kinetic energy plus potential energy plus internal energy multiplied by delta T plus W. And now divide both sides by delta T. Divide both sides by delta T. So you will get kinetic energy flow rate plus rate of potential energy plus that internal energy plus Q by delta T. Since time interval was delta T, so heat supplied to the system during that interval should be denoted by delta Q. Okay. And similarly, work done will be denoted by, instead of W, it will be denoted by delta W. So then in the left hand side, delta Q, delta T should appear, delta Q by delta T, and in the right hand side, delta W, delta T should appear. And the limit, you know that will be replaced by dW dt and dQ dt when delta T approaches 0. Now in the very next line, you can divide both sides of this equation by m dot also. By m dot also you can divide. So first time as kinetic energy flow rate, kinetic energy term, that will be half C1 square, like that. Okay. In the right hand side, minus P1 V1 term is there. You take that term in the left hand side. So in the left hand side you will get U1, so plus P1 V1. So this U1 plus P1 V1 is equal to what? It is equal to enthalpy. In the right hand side also U2 was there plus P2 V2 was there. So U plus PV again enthalpy. So I am not going to write all these things here. I think you know. In next video I will try to show you by writing equations. Okay. So this way the steady flow energy equation can be derived. Main thing is the development of the concept, how you should approach. And if in the open system there are so many inlets, say there are inlets, 2 inlets are there. So inlets are denoted by say 1 and 2, and outlets are denoted by 3 and 4. 2 outlets are there. Maybe 5 outlets are there. 2 inlets, 5 outlets. So for 2 inlets, suffix 1 and 2. For 5 outlets, 3, 4, 5, 6, 7. Like that, you can write this way. Just for simplicity, we have taken only 1 inlet and 1 outlet. So this is the procedure, or this is the approach to derive the steady flow energy equation. And by after derivation of steady flow energy equation, by using this equation, you can derive Bernoulli's equation, which you have found in fluid mechanics course. Okay. In the next lecture, I will show you how to derive Bernoulli's equation using this steady flow energy equation. Okay. If you have any question, you can write in the comment box. Okay. Thank you.